So the last talk of the day will be given by Oles Shtanko, from IBM, who will talk about criteria for stable quantum memories protected by engineered dissipation.
Hello, everyone. Thank you very much for joining me for this last talk of the day, and also thanks to organizers for giving me the opportunity. This presentation is for the work which is done in collaboration with my MDU colleagues. And whoops, something happened. No worries. It's just a slide. It's just a slide. So you're probably familiar with the screen, and a couple of months ago, there was a big noise about this error, which presumably caused by some faulty update. But also you can get the screen if your computer experiences an error in some of your bits. And if its bits has some important information for your computer, it can fail. And my question, maybe it's quite surprising, why we don't have it more often? Like, no, hear me out. I don't propose that we should have it more often, but we have billions of classical bits in our computer, and still we don't have it every minute, every second. We have it once for a while. And the reason for that is that our classical memories are extremely stable. And they're stable not because of some error correction we do. They have some design that makes them stable, and particularly if we have a classical bit. It usually consists of many elements. You may think about magnetic hard drive, consists of many domains. For electrons and semiconductors, a bit more complicated, but generally it forms some stuff of repetition code, and if errors come, they essentially flip some of the bits, creating a mess, but in general it's not a big deal because you can always use a majority vote to find out your value of the qubit. However, you cannot do it forever. Sooner or later a noise comes and makes all states are either 0 or 1, so you need a mechanism, and this mechanism essentially is a thermal bath that creates the excitation process. And if all zeros and all ones are essentially the lowest states of your system, energy states of the system, that creates a mechanism that brings you back to the code space, which can be described by a simple rate equation. For example, one you see in the bottom, which has two parts. First part describes the error process, and second part describes the process of decoding of your memory. And we know from a long time ago that if the temperature is low enough, such that the excitation processes win over excitation processes, you enter the phase which is exponentially stable in the number of elements. And maybe in the future, maybe in the far future, we'll probably want our quantum computers work using the same principle. And if we once create this computer, what will be a good model for this computer? And during the past few days, you've seen a lot of talks about Lindbladian dynamics, so that will be kind of our model for this autonomous memory, which consists of two parts. The first part is dissipation, that we model as essentially a very generic Lindblad equation, where EK are jump operators, which should be chosen based on your physical implementation. For example, if you have a multi-qubit code, that will be errors or for your individual qubits. While if you encode information in the bosonic degrees of freedom, and we have many beautiful experiments recently showing actually working principle, then that will be just excitation, de-excitation processes in your cavity. So finally, the recovery process should help you keep the information, and what it does, it just brings your system to the code space, and to define what is code space is just essentially a set of orthogonal states, which are not only orthogonal between themselves, but they keep being orthogonal even if they acted by some error. And we define an important quantity, which we call error radius. It's the minimal number of error operators you need to add to your state such that this code space state becomes non-orthogonal. And of course, that include your jump operators, its conjugate, and these pairs, which are elements of the limit equation. And what we want to expect, well, we have some expectation from this memory. In particular, one of the expectations that the logical error rate will behave something like what you see in the right, where C is some constant. And this means that if your error rate is smaller than certain constant value, you get exponential memory lifetime for in terms of error radius, which is usually proportional to the size of your system. And what I will argue today is that actually in reality, if your decoder is not special design, you have something on you see on the right. And the difference, of course, there is this L inside next to C and Y. And of course, for some decoders, we know that this is not very tight inequality, but I just want to convince you that if you don't design your decoder correctly, that's what you get. And what it means that your error of your autonomous quantum error correction will have the minimum value, which is usual scale theta 1 over gamma, and which means it's much weaker than active quantum error correction. And at the end, I will try to maybe make some criteria what you should do to prevent it. So now to show this, we use, and this result actually coherent with the previous works that show that autonomous memories are not very stable, though there are some examples which show that exist. So first of all, to prove that this is true, this is what we should expect, we use a very known trick, so-called time scale separation. First of all, for that, let's consider our noise error correction process without any noise, and make some basic assumption that every state converges to the steady state relatively fast with exponential rate, and the exponent restoration rate is our parameter g we call correction rate. And if this is true, then you can show that the evolution of density operator can be decomposed in two parts. One part describes your early time dynamics. It depends on details on Lindbladian. It's very complicated, messy. And the second part will be a long time dynamics, which brings you to the code space. And if we want our decoder to be a good decoder, this means that this essentially our map should be a recovery map similar to what we use in quantum error correction, which is equivalent to, say, measuring stabilizers and plotting corrections. So, and this brings us give us a very important tool to deal with this type of problems. And one of the first moves as a theoretical physicist is trying to kind of construct a spherical cow model, which will be this model. And to obtain this model, what I did, I just take my K of T operator and put it to identity. And for mathematicians, that will be just a special case. And for theoretical physicists, it will be kind of model that allows you to understand a little bit how this memory should operate. We call this global decoder because usually you cannot map this to any sort of local Lindbladian. But what it does is just take any error state and bring to the code space with the same rate. Okay? And we can also describe it with this very simple Lindbladian shown on the screen, where G parameter is somehow now empirical parameter, which we can compare them to other models. So now, why this model is important? It is important because we can easily compare it to the active error correction. If we take this Lindblad equation and make a stochastic unraveling, this stochastic unraveling will be a sequence of corrections separated by random times, which are sampled from Poissonian distribution. And this is very similar to active error correction, right? Except that in active error correction, we have fixed times. And this difference between fixed times and random times is that which makes a lot of difference. So, and to show it, we can make some very hand-wavy math. We can, for example, consider now error processes and recovery process together, then take a probability that two recoveries happen with time delay t, multiply by the probability that more than L errors accumulated between two corrections, and integrate over time. And that will give us probability for infinite sequence, what's the probability of failure between two corrections. And using this probability, we can estimate very roughly, it's not exact, but roughly estimate for very long times, what will be total probability of success. And it's absolutely, you can do this exactly and get the effective decay with effective rate. And this effective rate can be expressed in terms of your correction rate, number of qubits n, error rate gamma, and error radius. And if your correction rate not too large, you can compare it to exponent. And here's the thing, if you look at this expression, it has two ratio between correction and noise, and ratio between distance and number of qubits. And we know that for for all codes, error radius cannot be larger than the number of qubits. So this means essentially that you have a finite correction rate that you cannot overcome. So this is quite a hand-wavy math, and the reason for that is very simple. If you allow or randomize the time between corrections, there's always the chance that two corrections will be so far apart that it's guaranteed there will be an uncorrectable error between those two. Yeah, and that's the reason. And we have a proof, more like formal one, that for stabilizer decoders, stabilizer codes, and Pauli noise, there is indeed a lower bound on the error rate. It's a good question if we can extend it to non-stabilizer codes, though, but we believe that there is no good reason to assume that somehow magically decoders can overcome it if they become non-Pauli, however, non-stabilizer. Now, let me show just briefly assumptions about the upper bound I showed you just before. And that upper bound is proven for more general class of decoders. So we go back to our initial non-global decoder, and we make another assumption. We say, well, we declare our KFT to be part of a perfect decoder. And perfect decoder, it always reduces number of errors in your state. So for example, if you think about pure state, it always reduces number of error from high weight to low weight. And of course, there should be important disclaimer that real live decoders don't do that. There is always exponentially small probability of creating more errors. But as you increase the system size, most of decoders which you can come up with, they can be well approximated as perfect decoders. And for that, you can prove a separate bound, which you've seen before. The only difference is now Cn depends on number of qubits, and part depends on the contraction norm of your Lindblad operator, error Lindblad operator. And this notation means that it's taken over correctable error states. It's important because we also want to apply it for bosonic codes which have infinite Hilbert space. And most we hope that this norm scales with L. So best we can hope this C is 1 over G, which brings back us to square one that our if there is a threshold, it should scale down with a error radius, and essentially have a constant error, constant minimal error that we can expect. So one may ask a question, okay, that is band bound, but we know that there are good decoders. We know for dimensional toric code, for example, has this property that we can construct a local Lindbladian for which errors are suppressed exponentially. So, well, then you need this extra assumption to at least allow the global decoder. And one of these conditions will be the following. You can imagine your space of correctable error as an onion, where each layer describes a space which has k or more errors. So, and we find the overlap between them and just slice this error space. And then we require that our Lindbladian for recovery must act on each space with a strength which is proportional to the number of errors. And you then can show that probabilistically, if we have, for example, four-dimensional toric code where these syndromes are surfaces, and we have a lot of the surface bubbles, they contract with a rate which is proportional to the number of qubits in most of configurations, while for toric code, this is not true. Finally, quick question, do we need this actual exponential compression? So for example, I put this formula as a plot, and you see that if your ratio between error correction is, say, 1%, and you have L equal 10, you're already approaching machine precision. So in principle, as a complexity series, you may be very not satisfied by this result. But as a practitioner, maybe it's fine, right? So at this point, I would like to stop. Just as a summary, we show that autonomous quantum error correction is technically weaker than active error correction, and this might be OK. Thank you very much.
OK, we have time for questions. Okay, probably we're all a little bit tired. Maybe let's thank Oles again, but just hold on for an announcement. Let's thank Oles.